uh, we cannot find two electrons at the same time of same N, L, Ml, and Ms, so two electrons cannot be in collision. But it's possible to find two electrons of same N, L, and Ml. So now we have to use or to fill the electrons around the nucleus, and this is called the electronic configuration. First of all, we have to calculate the energy of all possible sublevels. For example, in level 1, we have 1s, and why we don't have, for example, 1p? Because we explained according to Schrödinger equation that if we have 1p, that means in level n equal 1, we have L equal 1. And this is incorrect because n could not be equal to L. So in level 1, we have 1s. In level 2, we proved that we have 2s and 2p. In level 3, we have 3s, 3p, and 3d. And in level greater than 3, in level 4, 5, 6, 7, we have sublevels S, P, D, and F. And maybe we have G. For example, for n equal 5. What are the possible values of L? 0, so we have 5s. 1, we have 5p. 2, we have 5d. 3, we have 5f. And we have another possible value, which is equal to L equal 4. So we have also 5g by theory. But we did not use the 5g orbital since the periodic table is composed of known elements. So we did not use 5g to fill the electrons. So the rule now, we have 4 types of orbitals in your curriculum, S, P, D, and F. We have to calculate the energies of these levels. For 1s, we have n equal 1, L equal 0, Ml equal 0. So we put psi 1, 0, 0 in the Schrödinger equation, and we calculate the energy of 1s. By the same way, we calculated the energies of all these sublevels in the figure. We found that the energy of 1s is less than 2s, less than 2p, then we have 3s, then we have 3p, and we proved that the energy of 4s is less than the energy of 3d. We have to pay attention for the meaning of 4s and 3d. 4s in energy is less than 3d, but 4s in distance, 4s is more distant from the nucleus than 3d. We have to pay attention the difference between the energies and the position. So we fill the electrons according to Aufbau rule, so according to the energies and not according to the position. So 1s energy, then 2s, 2p, 3s, 3p, then 4s, then 3d, then 4p. So 4s is filled before 3d, since the energy of 4s is less than the energy of 3d. Kleshkovsky makes a rule which is called the rule of arrows. We put in level 1, 1, 2s2p, 3s3p, 3d, 4s, 4p, 4d, 4f, and we start in the arrow of 1s, start here, and move along the arrows one by one. So the end of the first arrow is the starting of the second. The end of the second arrow is the starting of the third. So the electronic configuration according to Kleskowski, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10. So 4s2 is filled before 3d10, 4p6, 5s2, 4d10, 5p6, 6s2 till the end. So we obtain the complete Kleskowski rule, and now according to the number of electrons in the atom, suppose we have 26 electrons. So we fill 1s2, 2s2, 2p6, this is 10, 3s2, 3p6, 18, 4s2, 20. We need 6 electrons, so we end by 3d6. This is the electronic configuration of Fe56. This is the electronic configuration according to Kleskowski. So we calculated the energies of all sublevels according to Schrödinger equation. We apply Aufbau rule. We obtain a representation known as Kleskowski rule that makes easier the written of the electronic configuration. The ground state is the most stable state of the electron. This is the lowest energy orbital it can occupy. The distribution of electrons in the orbitals in an atom in its ground state is called the electronic configuration. Pay attention for the question. Sometimes they asked us to write the electronic configuration at the ground state, and sometimes they asked to write the electronic configuration at the excited state. The electronic configuration at the ground state, so we follow Kleskowski rule. And the electronic configuration at the excited state, so we have one electron that is excited from its initial place to another place, which is the excited state. And we will have exercises on the written of these two types of electronic configuration. Suppose we have helium Z equal to, so the electronic configuration is 1s2. What is 1s2? How can I translate this notation to a statement? Instead to write 1s2, I can say I have 2 electrons in level 1 from the nucleus, and the motion of these 2 electrons, so the probability of points to find these 2 electrons maximum is or has a shape sphere. So this is a notation. So 1 is the principal quantum number n, and the sublevel s, so L equals 0, and we have 2 electrons in motion. Instead, as 2, we have another electronic configuration known as the box representation or the orbital diagram. So 1s is one box. Inside this box we have 2 electrons, and 1 electron has a spin plus half, and the second has a spin minus half. This is Pauli exclusion principle. So the two arrows are in inverse directions. What is the valence electrons? The valence electrons are the electron in the outermost principal quantum level of an atom. So the valence electrons are the electrons on the valence shell, and the valence shell is the shell that is the most distance from the nucleus. So this is the last shell. For sodium, Z equal 11. So we have 1s2, 2s2, 2p6, 3s1, according to Kleshkovsky rule. The valence electron is level 3. So on valence shell is level 3. And in level 3, we have 1 electron valence. So what is the meaning? In the last shell, in the shell that is the most distance from the nucleus, we have 1 electron in motion. This is the statement. The inner shell or the core shell are the electrons between the nucleus and the valence shell. So we have level 1 and 2 are the core shell, and in the core shells we have 6 plus 2 plus 2, so we have 10 electrons core. Why we make the difference between the core electrons and the valence electrons? Because in the next chapter, in the chemical bonding, we will see that the valence electrons are responsible for the bonding of the atom with the other atom, and the core electrons has no role in the chemical bonding. For this reason, we can simplify the electronic configuration of sodium by subtracting the core electrons to the first or to the close rare gas. For example, 1s2, 2s2, 2p6, we have 10 electrons. This is the electronic configuration of neon. So we write the electronic configuration in other term or in other form: Na, sodium, electronic configuration of neon, and we have 3s1. This is the abbreviation of the noble gas neon. Example 2.1, write the short electronic configuration and not the detailed, and the short orbital diagram for each of the following. What is the meaning of short orbital diagram? So you write only the box representation of the valence electrons. Sodium, so we have neon 3s1, the box representation, we have 1 electron in 3s. Te, the electronic configuration Z equal 52. So we write only the valence shell. So krypton, the close rare gas for Te is a krypton with Z equal 36. So 36 and 2, 38, and 10, 48, and 4, 52. So we write only the box representation of the remained electronic configuration. So 5s, we have 1 box, 2 electrons, 2 arrows in inverse direction. Now D10, for D10. For D10, I have 10 electrons to be filled. So I start to fill 1, 2, 3, 4, 5. Then I redo the cycle 6, 7, 8, 9, 10. And pay attention, in each box, the two arrows should be in opposite direction. This is the Pauli exclusion principle. And the same for TC with Z equal 43. The electronic configuration, in the electronic configuration we have exceptions. Exceptions of Kliskowski rule. For example, consider chromium with Z equal 24. So the electronic configuration is argon 18, 4s2, 3d4, 18 plus 2, 20, and d4, so we have 24. This is the expected electronic configuration. To note that the electronic configuration, the stability of the electronic configuration can be studied according to Schrödinger equation. So if we use the Schrödinger equation, we found that the observed configuration is not the first, is argon 4s1 3d5 and not 4s2 3d4. So we have one electron of 4s that jumps to 3d. And as we know, when the electron passes from lower energy level to higher energy level, the atom should absorb energy. And in this case, the transfer from 4s to 3d is spontaneous. It takes effect without adding energy to the atom. So the experimental electronic configuration is 4s1 3d5. Why 4s1 3d5 is more stable than 4s2 3d4? In the level D, as I said, the best representation for an apartment is to fill all rooms by 2 students. So I say the apartment is completely filled. This is the most stable state of the apartment. If the apartment is not completely filled, I prefer, or we prefer, to fill 1 student per room. So the second most stable state for the apartment is when the apartment is half filled. And all other cases have the same stability. So for d orbital, the most stable state is to have d10. If we could not have d10, the second most stable state is to have d5. Look to 3d4. 3d4 is not completely filled nor half filled. So one electron of 4s passes from its initial place automatically to 3d, and in this case we have 4s1 and 3d5. 3d5 now become half filled. So 3d5 is more stable than 3d4. 4s2 or 4s1 have the same stability. So the electronic configuration observed 4s1 3d5 is more stable. So filled and half filled are very stable. This is the reason behind the stability of noble gas. Why noble gas are stable? Why noble gas did not give or gain electrons from outside? Because the electronic configuration of the noble gas is s2p6. And p6 is an orbital that is completely filled, so it's highly stable. In this case, when we have d4, it becomes d5. And when we have d9, it becomes d10. So the electron in d4 jump from s to d5, so we obtain s1 d5, and n plus 1 s2 and d9 become s1 d10. So as we will observe in the figure, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So this is filled. So one electron, look, one electron from 4s will pass to 3d. And pay attention that in case of orbital filled with one electron, the electrons should have the same spin. So all arrows will have ms plus 1. All arrows will have ms minus. All arrows will have ms plus half, or all arrows will have ms minus half. So we write the arrows in the same direction. This is the exception of the electronic configuration according to Kleschowski rule. Why the filled is the completely filled is the most stable, then the half filled, then the filled. So the most stable in d-type orbital is d10. Any electronic configuration that end by d tend to have d10. If it cannot have d10, so the second most stable state is d5. This is completely filled, this is half filled. And all others are called filled. d1, d2, d3, d6, d7, d8. Why I did not put d4 nor d9? Because we don't have d4. d4 become d5 and d9 become d10. The most stable in p orbital is first p6, then p3, then all others p1, p2, p4, p5. Why the completely filled and the half filled are very stable? This is due to symmetrical distribution of the electron. More the symmetrical distribution, more the stability of the orbital. And we have another reason that in case of half filled, for example, the electron can exchange its place with another electron. So here, for example, if we consider electron 1, he has 4 probability of exchange. It can pass to the second, so the second pass to the first. So we have 4 possibilities. As a rule, the orbital completely filled is the most stable, then the orbital half filled. The stability of the orbital increase when we have symmetrical distribution of electrons in the orbital. And the symmetrical distribution of the electrons in the orbital result in more number of exchange between the electrons, and this will increase the stability of the orbital.